Good morning, everyone, and welcome to our annual Christmas lecture in the physics department. Unfortunately, Paula Chadwick, the head of the department, is unable to be here this morning to give the welcome, so myself, as the director of outreach in the department, has been tasked with it. Our Christmas lectures are a tradition in the physics department here in Durham, and we try to give young people and not so young, or young at heart teachers at least, an insight into what we do. Durham Physics Department is the 5th largest department in the UK, and we specialise in lots of different areas, including particle physics, condensed matter physics, quantum physics, advanced instrumentation, space science, cosmology, and astronomy. And it's astronomy that we are turning to this year with a talk about the radio universe. Today's lecturer, Professor Leah Mauricio, did her bachelor's degree at the University of Michigan in the US of A, and while she was studying, she was in the US Air Force, rising to the rank of captain. After a master's degree at the University of Oklahoma, she went to Leiden in the Netherlands to do a doctorate in radio galaxies. After a stint at Oxford, she joined us in Durham just before COVID in 2019 and is now a professor and a UK Future Leaders Fellow. Leah works on galaxies that contain supermassive black holes and is particularly interested in how the black holes and the galaxies evolve together. To do this, she uses observations from all sorts of telescopes, but her speciality is making high-resolution radio observations of these extraordinary objects. She's currently using a radio telescope called LOFAR, and will be ultimately using the Square Kilometre Array, the biggest telescope ever built. And this will uncover more about black holes and the galaxies that contain them. She's going to tell you all about her work, as well as the surprising history of radio astronomy. When she's not at work, Leah likes to walk her dogs, to read and to sew, and her creations often have a distinctly astronomical theme. So please, let's give a big welcome.
Thank you. Thank you, Peter, for the very nice lecture. And thank you all for showing up. I see there's some Christmas spirit. I see some Christmas jumpers out there. I hope everyone is very excited to learn about radio astronomy. Okay, so I'm going to tell you today about the radio universe, and then we'll talk a little bit about the history, and we'll talk a little bit about those supermassive black holes that were mentioned, and finish up at the end with a little bit about the Square Kilometre Array. But in the process, I will also tell you about the telescope that I primarily use, which is called LOFAR, or the Low Frequency Array. Okay, but let's take a step back and kind of like place ourselves in the picture of what we're talking about. So, as you probably know, light travels in waves. So you have each color has its own wavelength. So if you take a prism and you have white light and you put it through there, they propagate differently through the prism and you end up splitting out the wavelengths, right? So you split from red down to blue. And each of these colors has a different wavelength. So the red is longer, the purple is the shortest, and this is the visible light. So just as a note, throughout this talk, I will talk about wavelength, but I will also talk about frequency, because these two things are related by the speed of light. So the speed of light, speed is meters per second, wavelength is meters, and frequency is per second. So this is the equation that relates them there. Oh, turn on the laser pointer. So this is the equation that relates them there. Speed of light is equal to wavelength times frequency. So that means longer wavelength means lower frequency, and shorter wavelength means higher frequency, because the speed of light is constant. Okay, so just now that we have grounded ourselves in the fact that light travels in waves, people can hear or not hear, I don't know, I'll just keep going. The visible light is only a very small portion of the entire electromagnetic spectrum. So light occurs all the way from radio wavelengths, which are very, very long wavelengths, very low frequency, up to X-ray or even gamma ray. So very short wavelengths, very high frequency. But we only see a very small portion of the spectrum. But what's happening across all of these wavelengths is still light. It's just not light that we can see with our own eyes. So this picture is also showing you what we can see from the Earth. So here we have the visible light that comes through this window, and these gray areas show you what the atmosphere absorbs. So the atmosphere will absorb some frequencies and not others. This depends on what is happening in the atmosphere, what it's made of. It will absorb some wavelengths, but not others. So you can see that when we go from ultraviolet up through gamma rays, this is all things you cannot see from the Earth. So this is why we have satellites. So X-ray satellites to observe X-rays, and ultraviolet satellites to observe ultraviolet light. And then when you go to the lower frequencies, the longer wavelengths, again, you have the same thing. So the infrared, again, not visible from the Earth, and same for the microwaves. But then we come to this window here. This is the radio window. So there's this huge range of wavelengths there in the radio regime where we can see things from the Earth, right? And so the radio waves can pass through the atmosphere and reach us, and we can observe them with telescopes on the ground. And this is what we'll be talking about today. Okay, so how did radio astronomy start? Let's say it's the early 1930s, and you want to send a signal across the ocean. So you have a telecommunications dish here in the UK, and you want to send a signal over to someone in Canada. Well, I mean, we already know, right? You probably have a radio in your car, which operates at radio wavelengths, and so you know already that radio is used for communications. But in particular, it's a low-frequency radio. So if you wanted to send like a high-frequency radio signal, you can do that over short distances, but there's something called attenuation. So signals will get attenuated, and this just means that whatever medium they're propagating through drains off some of the power of that signal, and so they can only reach so far. And this attenuation of signals depends on how far, the length that you're trying to send it, the length between these two dishes, but also the frequency. So higher frequency things become attenuated more quickly just based on this equation here, which tells you what the attenuation is. So high frequency may not reach it. And so people started sending low frequency signals. And so radio astronomy has kind of like really started out in this low frequency regime. So low frequencies have a lower frequency, which means less attenuation, which means they can reach further, and you can send a signal across the ocean. And so in the 1930s, there were all these companies that were developing these telecommunications things, but then they said, okay, well, we know our signals get attenuated, we're going to go to low frequencies, but what else might interfere with sending these signals? So Karl Jansky was tasked with figuring out what could be interfering with these signals. So he built this radio telescope, which was operated at the low frequency of 26 megahertz. It was called the merry-go-round. So you can see here this pole-looking structure here is actually the antenna. That's a dipole telescope, just like you have. It's just like a wire, like you have in a car. It's built on a track here. You can see the wheels. And so this thing could be turned to point it, okay? And so it looked like a merry-go-round, and that's what people called it. So Karl Jansky started observing the sky to see what there could be in terms of interference. And one of the things he found was thunderstorms. So the lightning is actually a source of radio emission. And so when there were really massive thunderstorms, then you would get interference from the signals. Okay, fine. So we know that thunderstorms, we can't control them, but we at least know when they're happening. And so we know that that might interfere with the signals. The other surprising thing that he found was what he called a shortwave His-type static. And this is the first detection of this static. This is just the signal from it. But he didn't know what this was. So it was an interference. It was kind of low level, kind of background, always there. So he had no idea where this was coming from. So what he did is he went out and he observed once a month for 24 hours and tried to track the motion of this signal through the sky. And so you can see the different curves here correspond to the different dates. So for example, curve 1 is the measurement in January. And you can see this is the horizontal component of the direction of arrival. So that's like where it's coming from in the sky. And this goes from 0 to 360. So some of these lines actually wrap around, right? Because when you have a circle, 360 degrees, so 0 is the same as 360. You go around the circle and you're back at the start. And so he started tracking things through the sky, in January, February, March, April, et cetera, et cetera. So he did this for a year and realized that the rise and set time of this signal, this His-type static signal, followed the stars. So this was, just the beginning of radio astronomy, because now you know you're looking at something that's coming from the sky. So this was the start. People didn't expect this. They were already looking at the sky in visible light, and now here Carl Jansky comes along. He's trying to figure out sources of noise in telecommunications devices, and found out that actually we can see a lot of the universe in radio. So people got very excited, and they started doing things like building telescopes in their backyard. So this is a telescope that was built by Grote Reber in the early 1940s. He literally built this telescope in the backyard and started mapping the radio sky. And this is actually the very first map of the radio sky that he made, that anybody made. So it looks not very nice, right? Because it's quite old. He had to point this telescope at the sky in many different places to map out the intensity in different directions, and then make this depiction of the sky. But this was a huge advancement, and you can see that there's structure in it. And I'm going to ask for crowd involvement now. Who can tell me what they think the structure might be? Anyone? Yeah, I see a hand maybe going up. No. So the cosmic microwave background it's a good guess, but the cosmic microwave background is in every direction. This kind of looks like it's all along one plane. Yeah. It is the Milky Way, right? So this is the galactic plane. And there are several different sources in it that you can, distinct sources. So this is the galactic center, and there's two diagrams here because he mapped out the northern and the southern hemispheres. And so this here is Cygnus A. That's actually, although it's along the galactic plane, it's an extragalactic source. This is the kind of source that we'll talk about much later on. And then Cassiopeia A, which is a supernova remnant. So supernova remnants are a source of radio emission. So this was quite exciting because people could look at this and they could say, okay, yeah, we know where the Milky Way plane is, and now we know that we see radio from it. So that's quite exciting. Okay, so how do we interpret what we're looking at, and how are we making these measurements? So we're going to talk now about how telescopes, the actual technology of how you make these observations, differ based on wavelengths, because radio is quite unique. So we're going to start out in the visible to optical regime, which you're probably most familiar with. You may have seen a telescope before. You've probably seen a camera before. If you have a smartphone, your smartphone has a camera on it. So there's two different kinds of, basic kinds of optical telescopes. There's refractors, and these were the first to be developed. So, when you think about Galileo and his telescope, this is the kind of telescope that he had. So this is where you have a lens, and that lens is shaped in such a way that the incoming light is then focused down to a specific point, and then you can see something very far away through the telescope. In modern astronomy, though, what we use now mostly are reflectors. And so this is actually an example of a mirror segment from a reflective telescope. So it's an example of what you have on the James Webb Space Telescope. But in reflectors, you have a big primary mirror that gathers all the light, collects it all up, and that sends it up to a secondary mirror, which then reflects it out of the path into your eye or a camera. So you can put a camera down instead of a person here. You put a camera, and then you can take a picture. Just like on your phone, if you're taking a picture, you have a camera. So the detector here is just collecting light. That light goes down to a surface, and then that's recorded. So you're recording an image. X-ray is the same in that you have mirrors and you're taking a picture of the incoming light, but it is a little different because X-rays are much, much higher wavelengths. There are much shorter wavelengths, much higher frequencies, and so they're much higher energy. And so you can imagine, like, if someone's running around and they're not going very fast and they hit a wall, they're going to bounce off of it, right? That's like optical light. Now, if someone is like supercharged and running super fast and the wall is thin, they're going to just go plow right through the wall. They're not going to bounce off of it. But that same person who's running really fast, if they're running alongside a wall and just kind of like bump into it, they'll be deflected. So it's the same kind of thing with X-rays. They're so high energy that they would just pass through a mirror if they hit it straight on, but they get deflected if you have kind of like things that just help guide them. And so this is called, where you have the X-rays coming in, and then you have these concentric mirrors, and these mirrors are kind of like helping channel the X-rays down. So they kind of graze along the mirrors, and they can graze a couple different times, as you see in this diagram, down to the focal plane. So the detector is still the same kind of thing. You're still taking a picture of all of the photons that are coming in, and taking an image. And it's based on mirrors, but the mirrors are very different. When we move to the infrared, then you're still using mirror technology. So this is, for example, the Spitzer Space Telescope. You are still looking at these wavelengths that are now just a little bit longer, but it's very similar to an optical telescope. So I will just show you that you do actually see something a little different. So I'm going to ask everybody to wave for me. Yeah. So this is what you might see with an infrared telescope. And then I can also show you. Yeah. Okay, so here now you're seeing everybody can wave again. So now you're seeing what you see in optical, but then also what you see in the back, in the surrounding, and now you can see also what you see in infrared. So you're seeing the same kind of things. You're seeing the exact same things, but it is a very different kind of picture because you're looking at different wavelengths, and so you're getting different information. So the infrared is telling you something about like how warm something is, whereas the optical just tells you what like kind of it looks like invisible. Okay. Okay, so same kind of deal though. You have some mirrors, you have a detector, you record an image. Radio telescopes though are very different because they don't have a detector at the telescope that takes a picture. The radio telescopes measure the incoming electromagnetic waves, and they measure those as voltages, and that those voltages contain information about the electromagnetic waves that we then convert into images. So we are not taking a direct picture in the radio. We're measuring voltages at a telescope and then turning those voltages, which give us information about the incoming wave, the amplitude and phase of that wave. We turn that into an image. Okay, so just to give you an example of a radio telescope, well, I have an example of a radio telescope right here. This is a single antenna element of the low frequency array, or LOFAR. This is actually a real antenna. It's broken, which is why it's here and not out in a field somewhere. We'll talk about LOFAR a little bit later. What you're probably more familiar with is something like Jodrell Bank, which is a very massive 250-foot telescope out by Manchester. And so this is one of the UK's premier radio telescopes. So why is this thing so big? Well, it's all down to resolution. So if you take the equation for resolution, so here is your resolution, and this is equal to your wavelength divided by d, which is the diameter of your dish. So remember, radio waves are much longer. They're a longer wavelength, and so you need to have a bigger dish to collect those longer wavelengths and have good resolution. So when lambda goes up, so does d, if you want to keep this number, which is your angular resolution, small. So the goal, if you want to see fine structure in things, is to make theta small, so you have a small, high resolution. It's kind of counterintuitive, right? We want to make this small, but we call that an increased resolution, right? So that just means you can resolve finer structure. Okay, so we have to make a really big dish. So If you want to make your resolution better, because you've already built a 250-meter dish, or 250-foot dish, and then a diameter dish, and you want to get better resolution, there's two ways you can go about it. Well, there's three ways you can go about it. The first one is you can make a bigger dish. But this is already massive, right? And so people have made slightly bigger dishes, but it gets to a point where you just can't make bigger dishes anymore because it's just not practical in terms of like engineering or the logistics that you need to do this. You could go to higher frequency, and people did this a lot when they first started out in radio astronomy. So radio astronomy, remember, started out at 26 megahertz, and then people started increasing frequency to get better resolution. And the third option is something called radio interferometry. So radio interferometry is where instead of building one dish, you build many, and then you have an array which gives you a bigger effective lens. Okay, so how does radio interferometry work? If you no longer have just one telescope, but you have, let's say, two. So here is your astronomical source. Here are your two radio telescopes. So the source emits radiation. This is done isotropically, so that means it's the same in every direction. So that means you're emitting radiation in a sphere. This sphere goes out, the sphere of radiation goes out, and it propagates towards the Earth. And by the time it gets to the Earth, that sphere is so big that you can kind of approximate it as a plane in between the two antennas. Okay, so this is called the far field approximation, and this is what makes everything work because the maths then become simpler. So essentially, the sphere comes out, of radiation comes out, and then it hits this telescope first, just based on the geometry of the situation. But we know which direction we're looking in. We know exactly where our antennas are. And so we can actually calculate what the time delay is using the speed of light and our knowledge of the geometry of the system, how long it will take that same wavefront to reach the second telescope. So we can then calculate, we can take this delay out in our calculations and say, okay, this measurement at time 0 for telescope 1 and this measurement at time 1 for telescope 2 are actually measuring the same wavefront, and you can put that information together. We also need to know the distance between the antennas, and now this is what sets your resolution for interferometry. So rather than the size of the dish, now you're talking about how far apart the dishes are. And you can imagine that I can put antennas much, much further apart than 250 feet, right? So that's how you can improve your resolution. Okay. So this is just an example of a radio interferometer. This is the Very Large Array in New Mexico. And so you can see there's 27 dishes in this array, and they're arranged in this Y shape. And you can maybe see the tracks here because the VLA is actually configurable. So they have a machine actually that comes out and can actually pick up an antenna, move it out to the tracks, move it down, and move it to the next antenna pad. So this can go from something that is only a couple of kilometers compact out to 11 miles, which is about 20 kilometers. So now rather than having your resolution be set by the size of the dish, now your resolution is set by the size of the array. Okay, and so now we're going to do another little interactive part. So we're going to do a demonstration. So I need 7 volunteers to come down and pretend to be a radio telescope. So seven volunteers. Yeah, come on down. Close this. Okay, so you can be a radio antenna. You can be a radio antenna. Take one. Okay, So we're going to pretend that we're the VLA. So here, what I've got here is just like a little interactive thing to show you how radio interferometers work. So here is the VLA configuration. This is the most compact configuration. So I want you guys to organize yourselves to pretend you're the VLA. Almost there, almost there. Yeah. Okay, all right, that looks pretty good. Okay, you can hold your antennas up. You can be an antenna. Right, okay, great. Okay, so this is the VLA configuration. So now I'm going to load an image. So we're going to pretend this is what we're trying to observe. Okay, so this is what we're trying to observe. This is my dogs. So I thought this might be a nice, fun example. Okay, so this is what is really in the sky if we're observing an astronomical source. And then add, calculate, and plot. And then what you see here, I've got to do this. Right. Okay. And so then what you see here, this is the information that a radio telescope would measure. So this image is related to this image here by a Fourier transform. So you may or may not have come across Fourier transforms, but it's basically how you relate one function to another with an integral. And so this is what you would measure with a radio telescope. But this is what you would measure if you had an infinitely large radio telescope. So you can see that even though we're simulating a bigger dish here, there's gaps. So if I stand right here, there's no antenna right here. And so that means that your sampling is incomplete. So you're simulating a bigger dish, but you can only simulate parts of that bigger dish. And so your sampling is incomplete. And that's what you see in this top middle image here. So this is your sampling. So with this configuration, you can fill out only part of what we call the UV plane, which is this. And so you can only get information from the parts of this where you have a red dot, okay? So that means you have incomplete information, so we will never be able to reconstruct a perfect picture. Okay, so we've imaged with the VLA compact configuration, and I'll show you what that looks like. So here is the resulting image here. Okay, so you can see there's shapes. You know what we're trying to look at, but from this image that the telescope sees, you can kind of say, like, okay, there's some shape, there's some things going on here, it's not just plain, but you can't answer scientific questions like, how many dogs does Leia have, or what kind of breeds are they, and what are they doing, right? Because you can't see all of the details. Okay. So now we're going to pretend we're the VLA B configuration, which is much larger. So here's the VLA B configuration. So you can see that we've changed from like being a kilometer in either direction now to just over 11 kilometers. So you have to spread out now. You may not be able to maintain the Y shape, but you have to kind of spread out. Bigger, bigger. You can go up the aisle, maybe. Maybe start going up the aisle and yeah. Okay, all right, great. Yeah, okay, all right, that works, that works. Okay, so now we're much bigger, right? And so you can see this is a much bigger area that we're covering. And so that gives us a larger effective lens. And so now, if we do the observation. So now you can see the coverage has changed. So the red is what the D configuration would give you. And now the blue is what you get with this larger array. So you're covering more of this space. So you're able to sample more of it. So you can reconstruct more of the image. And then you can see now it's not perfect, but we get a much, much better image with much higher resolution. And so now this kind of image you can start to do science with. Okay, all right, thank you very much. You can put your telescopes back. You can have a sticker if you want as well. Yeah. Okay. All right, backup slides in case nothing worked. Okay, so that's the general idea for interferometers. There are many different kinds of interferometers. So the one in particular that I use is the International LOFAR telescope. So this is a phased array of dipole antennas, which is dipole antennas look like this. So rather than the dishes of the very large array, you just have these wire antennas. These are actually the receivers. Okay, so this is a little bit of a different technology. And the reason that we do this is because we're operating at such low frequencies that to build a dish for an interferometer at these frequencies is just not technically feasible. And so we simulate having a dish by using the same kind of trick. We build loads and loads of dipoles in a field. So there's 96 dipoles in a field. And then we combine all the signals from those together and pretend that's a dish in our regular interferometer. And so that's how LOFAR works. And so you can see a field of those antennas here. So this is the low band antenna, which operates just under the FM radio band. There's also a high band antenna, which is protected from the elements, from the rain and wind and snow. And that's in these covers. And then you can see here is a field of 96 dipoles. So this is the same as one dish in the very large array kind of thing. So you can see there's 1, 2, 3, 4, 5, 6 stations here, and that makes up the heart of our interferometer. Now, unlike a dish, I cannot move this dipole and point it. I mean, I can move this one because it's not attached to the ground, but in the field, they're actually attached to the ground. So we point these telescopes electronically. So here's our source, here's our two telescopes, and they can't move, but we do know where the source is that we want to look at, and we know the geometry of where our antennas are. And so what we do is we add that virtual time delay in, which effectively moves the telescopes into a plane that is orthogonal to the direction along the line of sight that you want to look at. So we're pointing the telescopes electronically by adding information into the signal path based on the geometry of what we want to look at and where our telescopes are. And so this means that LOFAR is a little bit of a different telescope. It's what we call a software telescope because everything is just done on supercomputers. And data sizes are huge because you have to do all of this maths, all of these calculations, and you have 96 dipoles, so the data rates coming off of those are very large in a station, and then there's 52 stations. And so the data sizes are very large. Everything is done on computers. There's no moving parts in the field. So very, very low kind of like engineering effort, but very, very high computer science effort. Okay, but what I've just showed you is only the very central portion of the International LOFAR telescope, the LOFAR array. There are stations that are spread out all throughout Europe. So standard operations, when we first started out observing with LOFAR in 2012, used just the Dutch stations. So this is what we call the Dutch array. So we just combined the information from these antennas, which gave us about 6 arcsecond resolution at 150 megahertz, which is pretty good for a radio telescope. But what I've worked on over the last decade is all of the kind of like techniques, the calibration techniques, and how we just do everything, all of the data processing for the entire array, including all of the stations in Europe, which then improves the resolution by a factor of 20. So 20 is a big number. I mean, it's a big number to me. It's hopefully it sounds like a big number to you, but that doesn't really give you a feel for how much the improvement is. So coming back to this picture, I mean, you already know the answer, right? This is my dogs, but if we pretend this picture was taken by the Dutch stations, if I improve the resolution by a factor of 20 by going out to the longest baselines and increasing the size of my array, this is what I then get. This is the factor of 20 improvement that you get in the image. And so that's just absolutely phenomenal to be able to study all of the detail in the sources that we want to look at. Okay, so what is it that we actually look at with these kind of telescopes? Well, let's start with what what do things look like in general that we're looking at in the sky? So here is a galaxy called Centaurus A, and this is what it looks like in the visible to optical. So you can see the light from all of the stars in the galaxy. You can also see the dust that's blocking the blocking the light from the center of this galaxy. If we look at this in the X-ray, then we see there's a lot of kind of like diffuse, fluffier gas. And if we look at it in the infrared, you can see it looks different again. But now the kind of like dark parts in this image are starting to be the light parts in this image because you're looking at that warm dust in the infrared. But these two images, visible and infrared, look kind of similar. And X-ray also kind of similar, right? It's like it's brighter at the center, and then you have some more less bright parts on the outside. But this is what Centaurus A looks like in the radio. Totally different. And that's because we're seeing something really, really different there. So what is it that we are actually looking at when we look at things in the radio? Centaurus A has what we call an active galactic nuclei. So this is powered by a central black hole at the center of the galaxy. That black hole is actively feeding on the gas and dust in the galaxy. So all of this material is attracted by the gravitational pull of the black hole at the center. It can't all cram onto the black hole at once, but it wants to. And just to say that this central black hole, even though I'm calling this a supermassive black hole because it is supermassive, it is a very, very small portion of this galaxy. So Centaurus A is about 60,000 light years across, but what we're talking about now, as the active galactic nuclei, or AGN, is only about 30 light years across. And this it's such a small region that we can't directly image it. This is this is an artist's impression. But in this region, right, we have this central supermassive black hole. So all this material is coming down and trying to cram onto the black hole all at once to make the black hole bigger. It can't do that. And so what you end up with is what we call an accretion disk. So if you think about like water trying to go down a drain, it can't all do it at once, but it's got some motion. And so when it comes to the drain, it comes and it starts to swirl around the drain to spiral in towards it. It's the same kind of idea here, where all of this material is coming in, and it sets up into this kind of rotating disk around the supermassive black hole. Because all this material is getting crammed together, it's getting very, very hot, and it starts to emit in the visible and optical wavelengths. And so we can see that in our observations. Above this accretion disk, we have a very diffuse gas that's very hot. This is much, much hotter than the accretion disk itself. And so this emits at the X-rays at much higher frequencies. Around this, you have a dusty ring. And so we call this a torus. It's just kind of like a donut-like shape of dust that's collecting outside of the accretion disk. And we see this in the infrared. So not every galaxy has an active galactic nucleus. Only about 10% are active at any given time. And in these AGN, only about 10% of the time we see radio, but when we do see them, it is powerful radio jets, right? So here you have, this is all powered by the supermassive black hole. And this is a galaxy called Hercules A. So this is an optical image overlaid with radio. This is the optical galaxy that you would see with the visible light. And then these are the radio jets. And the person who made this image is actually sitting in the room right now. But you can see how big the radio jets, right? So Centaurus A, right, the galaxy was about 60,000 light years across. This is almost 2 million light years in extent. So, I mean, what's happening is this material is coming in, and for some reason, this jet gets triggered, and it's like turning on a really powerful garden hose, right? And this material shoots out from the supermassive black hole in both directions, and then we see emission in the radio. So the emission process that's causing this radio is synchrotron emission. So these jets have ordered magnetic fields, and you have free electrons, so which are slightly negatively charged, right? And so they spiral around the magnetic fields. When you spiral, you're turning. Turning means acceleration. Acceleration means that you can produce radiation, and that's synchrotron emission. So when we see these in the radio, we know that there are magnetic fields, and we know what's generating the radio emission. So these jets are like cosmic fountains that can impact how galaxies grow. This is just a simulation of a jet, and it's not propagating through any medium. It's just going out. But you can imagine if you put something like this in a galaxy where you have stars and dust and gas in the way, that it's going to go out and it's going to hit those things and it's going to make a difference, right? It's going to maybe heat some gas. It's maybe going to push things away. It's really going to change what that galaxy looks like. We also see that these jets make an impact on a much larger scale. So this is a LOFAR observation of a particular AGN. This is what it looks like with the Dutch array, and this is what it looks like with the full international array, so improving that resolution by a factor of 20. It is the central galaxy in a galaxy cluster. So just as a reminder, the galaxy is really just like where this bright dot is in the middle, right? So these jets extend far beyond the extent of the galaxy itself. And this image here is showing you the X-ray hot gas in that galaxy cluster. And what you can see is the orange is where the hot gas is. And what you can see is that the radio jets have actually pushed this gas out of the way, right? So you can see these cavities, these depressions where there's no longer any hot X-ray gas because these jets have gone out and pushed that gas away. So not only can these radio jets impact the galaxies in which they live, they can also go out further than the galaxies themselves and start to impact the overall environment, so the larger environment, which then has implications for other galaxies that might be nearby. So radio jets also help us understand the first galaxies, not just the environments of those that are close by. So this is an example of a very, very distant radio galaxy with these radio jets. This is what it looks like in the visible light. This is what it looks like with Dutch LOFAR. And this is what it looks like with the international stations. So here's the galaxy, and then you have these radio jets. They are very, very distant, so it's very hard to look at this low surface brightness emission, which is why you don't see as much in the high resolution image. But this galaxy is from a time when the universe was very young, so way less than a quarter of its current age. And so by studying these things, right, we know that these radio jets are generated from supermassive black holes. So we can go out, we can look for them in really, really distant galaxies to try to understand the supermassive black holes that have generated them. And this is actually a big problem for us in astronomy right now, because we see loads and loads of supermassive black holes very early on in the universe. And it is a challenge to grow black holes to be that big, that quickly, so early in the universe. And this is something that JWST is uncovering, but also radio, because we've been discovering these very, very distant galaxies with radio, because they generate these really powerful radio jets for a very long time. So putting this together, we here at Durham, we also do simulations of the universe. So this is the Eagle simulation that was run here at Durham. And so this is basically, we take all of the physics that we think we understand about how things work, and we put it into a model of the universe, and then we let it evolve forward. And so we know that these radio jets have an impact, and you can see the effects of this going off in the yellow here as these AGN outburst. We don't have quite good enough resolution to actually put in jets, but we put in the effective jets. And so we can study, using simulations as well as observations, how these radio jets are impacting the universe and how it grows. Okay, so now that we know what's causing the radio emission, I just want to come back to this optical image of this is part of the Eleus N1 deep field, which is just a part of the sky that astronomers have all said, okay, we're going to look in that direction with all of our telescopes for a really long time to get really deep data. And so this is the optical image of that. And now here is the radio image. So coming back to that very first slide, which you probably looked at and was like, oh, it's kind of pretty, but I don't really know what's going on. This is what's going on in the radio. So again, here's the optical, and then here's the radio image of that exact same portion of the sky. And so you can see here, again, you have, this is one set of jets from a supermassive black hole, which is in this galaxy. Here's another, here's another, here's another. They're just everywhere. And so we're able to study these supermassive black holes all across the sky. So this is a very nice image that was made by LOFAR with high-resolution imaging. But you can see there's still some noise in the background. We're not seeing as many galaxies in this as we're seeing in the optical image. And so how do we then improve that? Well, we need better data. We need deeper data. And so for that, we are building the Square Kilometer Array Observatory. So this is an intergovernmental organization with many different partner countries. And there's two portions to the Square Kilometer Array Observatory. There is the SKA MID, which is being built in South Africa, which is dishes. And so this is at higher frequencies. And then there's something that looks like LOFAR, and this is being built in Australia. This will operate at low frequencies. And the global headquarters are actually here in the UK at Jodrell Bank, which I got to visit last week, which was quite fun. But this is going to be a giant array. You can see the number of antennas, the number of dishes there. And I already told you LOFAR is generating data sizes that are like, for a single observation, it's like terabytes. The SKA is expected to generate 700 petabytes of data per year. This is just like a massive amount. So you absolutely need supercomputers. You need computer science. You need people who can do clever things with algorithms to help us process all of this data. And for that, I'm involved in the SKA Regional Center, which will help do this and then interface with the astronomers. So all of the data processing is done on supercomputers. And I actually have some stickers from the SKA Regional Center if you want to come and take them at the end. So this will be a massive, massive data challenge, but it will be worth it. So this is where we are in terms of the SKA at the moment. We are in construction phase. So we're building the antennas, and then this will be followed up by commissioning, which will happen very shortly for the mid and is already starting to happen now for the low. And so commissioning is basically like checking out this, turning on the system, what you've got already, checking it out, making sure you're getting things that you expect, making sure that it's operating to the engineering specifications. And then towards towards the start of 2027, for the low dishes or the low array and the 2029 for the mid dishes, we'll start science verification. So if you're interested in radio astronomy, right, and you go on to do an undergrad degree and then a PhD, you could end up starting to work on some SKA projects. So science verification is where we basically point the telescope at some known radio sources in the sky and say, okay, do we see what we expect? So yes or no. So this is basically to check that we see what we think we should see and that the telescope is working properly. And then science operations, where people can propose for time and say, I want to look at this object, and then it gets evaluated by a committee that says, yes, that's a valid science project. That is expected to start in 2030. So because the SKA low is already working, I thought I would just show a little video. So this is the SKA low telescope site. You can see there's 6 dishes in this, and this is part of the core. So there are 4 dishes that are already operational. There's these ones. And in March 2025, they made the first observation with SKA low. And now, from here on out, what you're seeing is simulated data with more and more telescopes as more and more telescopes are added to the array. So you can see on the left-hand side, the telescopes that are popping up as they're being built, and what impact that has on the data as we're filling out that interferometer. And so this is what we expect from 2030 and beyond. And you can see just like the number of sources increases. And maybe I'll just see if I can go back. Yeah. So you can see the number of sources increase as we add more and more antennas. And really, you can see the wealth of information that you'll get from this incredible new facility. Yes, can we go to the next one, please? Yeah. Right, okay. So in this talk, we first started out in the 1930s with the discovery of radio waves from the sky. We talked about the development of interferometry, and you got a nice live demonstration from our volunteers. Thank you for that. On how increasing the resolution can help you, how you can use interferometry to increase the resolution to help you understand what it is you're looking at. We then talked about continent-sized software telescopes with huge data rates like LOFAR and the upcoming SKA. We also talked about active galactic nuclei, which is what I and my group here are using these radio telescopes to study. And we're really, everything that we have done with all the technology and all of the advancements we're using to study the beautiful radio universe. And so hopefully now, at the end of this talk, you can look at this radio image and understand what's going on there and see that there are supermassive black holes everywhere we look in the radio universe. Yeah, I think that's all I have to say. So I'm very happy to take any questions now. Thanks. Questions? Yeah? I didn't see any other hands, so they've got time.
The size of those jets being kind of similar to the distance between some galaxies, is it possible that those jets can affect the motion effects?
Yeah, it is possible. And we do see this sometimes that I've actually just read a paper draft this morning about a jet that is potentially impacting with another galaxy. The thing is, though, I mean, even if you look at optical images and it looks like it's absolutely crammed with galaxies, they're actually quite distant. So for you to find a jet that is actually hitting another galaxy is very, very rare, but there are examples of it happening. And in that case, it can even help break the galaxy apart, and which, of course, then impacts its evolution. Yeah, it's a good question. Any other questions? Yeah.
When doing interferometry, does the actual diameter of each individual telescope make as big a difference as just increasing the size?
That's a great question. So yes, the size of the dishes matters. It matters less, but the size of your dish sets your total collecting area, and that sets the sensitivity. So if you put a bunch of tiny dishes all around, right, you can either put loads and loads and loads and loads of tiny dishes, or you can put a few larger dishes, and those can have equal collecting area or equal sensitivity. So interferometry is kind of a little bit of the Wild West in that it's really what do you want to optimize, because there are so many dimensions that you can optimize in. You can optimize in how you lay out the antennas. The VLA has chosen a Y configuration, but as you can see, it's different for the SKA. You can choose the size of your dishes. You can choose the number of your dishes. All of these things will impact the final observations that you can make differently. And so really, you start from what is it that I want to do with this telescope? So what do I need? Do I need to be very sensitive to very high resolution? Do I need to be very sensitive? And then you work backwards from that and start to make decisions about how you design your array. That's an excellent question. Thank you. Yeah?
With the radio images, there are rates from visualize the depth and the kind of angle that the jet coming out at.
Oh, no. The answer, well, so yes, you can do it if you add information from the optical, right? So with optical, you can get an idea of how distant something is from the redshift. So we look for emission lines in optical spectra, and we see how far they're redshifted from what their rest frequency is, and that tells us how far away the galaxy is. But from radio alone, you cannot do it. But that's a great question. Yeah, and the gentleman next to you. The SKA, yeah?
Yeah. The transom antennas such a regular pattern. Is there a reason behind that? Is it more?
It's just to optimize the coverage that you get in that Fourier space, so that when you go to Fourier transform that into an image, you have better coverage of what you want to see in that image. So like I said, there are many different ways to optimize this. Some people have suggested that like pseudo-random layouts are much better actually than regular layouts for interferometers, and that's kind of where people seem to be going. Some of it though will be, in the case of the SKA, will just be driven by where they can get permits to build. So sometimes choices are made based on that, right? So you know you want like 100 telescopes over this giant area, but then you have to go out and talk to all the people who own the land and say, can I build a telescope on your land? Can I buy your land? And so sometimes you have like an overall design that you're aiming for, and then sometimes it has to be changed for just practical reasons. Yeah. The hardware of the antenna, yeah. Oh, that's a good question. So I think the overall SKA costs are in the kind of like tens of billions, but that includes a lot of the computing, right? Because for an interferometer, you absolutely have to have a supercomputer to put all the information together. It doesn't matter if it's, the SK, which is generating that much, like 700 petabytes of data a year, or something like the Very Large Array, which generates much less data, you still have to have a computer that takes all the information from all of the dishes and puts it together, so correlates the information from each pair of antennas in the interferometer. So I don't know how much the hardware itself does cost, but I can tell you that something like LOFAR, the low frequency array, is about €1.5 million for a station, which is really low cost when you compare it to something like the extremely large telescope or even the SKA, because the hardware is very simple, right? I mean, this is just like, it's just a pipe with a bit of plastic at the top. There's some electronics in here. Those are broken. That's why this telescope can be here with us today. But then it's just wire dipole, so that's much cheaper. Yeah. Any other questions? Okay, well, I'm happy to stick around if you want to come up and ask me a question individually. Thank you very much for attending, and I hope you have a great Christmas.